Assalamualaikum warahmatullahi wabarakatuh. So we start with chapter number 2, molecular force in biological structure. So we want to see what are the force that will affect this biological or this polymer in biological uh, protein or nucleic acid. Okay, so the molecular force will govern how a protein fold and which of its different conformation will predominate. Okay, so we'll govern this one, and it also determine the structure of nucleic acid and lipid bilayer. Okay, so it will see which it decide how the conformation of the nucleic acid and the lipid bilayer or the protein. And also it will drive the association between macromolecule and the ligand, okay, or the virus or the oxygen or whatever. Okay, so how it will do the doing the associations, whether it can associate or it will be hard to associate with between this A and B. Say A is macromolecule, B is our ligand, for example. Okay, so we have a lot of force. So the first one is the Coulomb force. These are just like our EM, electromagnetic one. So the Coulomb law, point charge interact with a potential energy that is inversely proportional to the distance of separation, R, and directly proportional to the product of the two charge Q1 and Q2. Okay, so this is in our physics one. Also, we have this one. So U equal to Q1 over Q1 Q2 over var epsilon R, or 1 over 4 pi epsilon not Q1 Q2 over R. Okay, so where Q is the charge, R is the resistance, and var epsilon is the electric constant. Okay, so we can see that here when the molecule is near to each other. Okay, so we have a high Coulomb, low Coulomb energy, or low Coulomb potential. Okay, but when R is 4, then we have high Coulomb potential. Okay, so here we can see here, you can see that when Q increase, U increase, the potential increase. When R increase, U decrease. Okay, so we can see here. And var epsilon depend on how easily the molecule in the environment are polarized. So when var epsilon increase, dielectric increase, U decrease. So we can see here when this is big increase, U decrease. And the value for dielectric constant is between 2 and 80. So these are vacuum, these are the water molecule. So these are the example. Okay, and HCl in water with var epsilon for the dielectric constant for water is 88. The potential is only 1.3 kilocalorie per mole and is greater than 2 RT, the thermodynamics constant. So for that it will, and NaCl will dissociate and dissolve in the water. Okay, so it will not be like a salt, but it will be in ion Na plus and Cl minus. Okay, and on the other hand, if the value of var epsilon is equal to for of hydrocarbon, so make electrostatic interaction within the hydrophobic core of protein and membrane enormously strong. Okay, so we can see epsilon uh, 2, so U increase. Okay, so then this one, the potential will be increased. So what we can say is that here for the Coulomb potential that affect the structure of the biomolecule is that in her homogeneous dielectric, it is easy to compute the electrostatic energy as a sum of U over all pair of charge. Okay, so if our dielectric is only water, then it's easy to calculate. But if we have in the solution we have water, we have uh, oil, we have the alcohol, then it will be the sum quite difficult because the relative constant will be different for each solution. Okay, and so here we can see that, however, biological systems are really homogeneous. So we have water, we have the uh, oil, we have the alcohol. So and special variation in dielectric prevent the simple use of the Coulomb potential in most situations. But in here we can, if only three solution, so we can just see that u equal to u1 plus u2 plus u3. u1 for water, u2 for oil, u3 for the alcohol. Okay, but if we have a very lot solution, then it will be quite difficult to do the calculation. Okay, and the distribution of this oil, water and alcohol. Okay, so we have this. The electric potential in a system with different region having different electric constant can be worked out by solving the Poisson or closely related Laplace equation in our PDA. Okay, probability and data analysis with boundary condition given by the specific of the geometry of a particular problem. Okay, so we can use that equation. And for a simple system with planar, spherical or cylindrical boundaries, some standard mathematical method can be employed. Okay, so this one is just our math method and advanced math method. Okay, so we have planar. So what is the boundary condition? Spherical, what is the boundary condition? And cylindrical, what is the boundary condition? So we can modify it so that we can calculate the Coulomb potential. And for a complex and irregular geometry, it will usually necessary to use a computer to solve the equation numerically. Okay, so this one to calculate this Coulomb potential. Okay, so from the thermodynamic stand of view, okay, the Coulomb potential is a electrostatic interaction between uh, the 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 ion, okay, or the charge, okay. So for thermodynamics, we have enthalpy and entropy. So when enthalpy is measured, the value is often erroneously attributed to electrostatic interaction and hydrogen bond, okay. So this one, electrostatic interaction and hydrogen bond, and large entropy are usually attributed to hydrophobic interaction, okay, chaos. So in thermodynamic term, it is free energy Gibbs rather than a simple potential energy U to be equated with the enthalpy. Okay, so here in, for example, in water, the Coulomb force is entropy S different. So this one S equal to G1 over var epsilon partial epsilon over d partial T. So when E is constant, so if this is constant, then this differentiation will be 0. So S equal to 0. But when uh, var epsilon depend on the temperature, so meaning that the dielectric depend on temperature, so this entropy also will change. Okay, so here if at T equal to 300 K, so S equal to minus 0.00046 G. So G equal to, from our thermodynamic, U plus the pressure or volume minus Ts. So Ts equal to minus 1.38 G. Okay. So here we can see that the entropic attribution is greater than the free energy itself. Okay. So S over S divided by S equal to 1 minus 1.38 G divided by T. Okay, so S is greater than G. So the conclusion for this potential, enthalpy opposes the attraction between oppositely charged ion in water and the entropy that pull them together. Okay, so the entropy, the movement of the charge, will pull the charge together. The molecular interpretation of this surprising result is that the soft ion restrict the rotation of the surrounding water molecule. Okay, so it will do the hydrogen bond with the water, so it will restrict the rotation of the water molecule. The work done on this water molecule offset the work done by the ion on one another, so that the Coulomb potential expressed as a balance between ion-ion and ion-water interaction. Okay, so these are it work ion-ion and ion-water interaction. So that is the Coulomb potential. So the next one is we have the electrostatic self-energy. So if we have one ion in the solution, okay, so that ion will vibrate. So when it vibrate, it will produce this electrostatic energy. Okay, or in our EM or in our physics, so we have the Gauss law. Okay, so these are just Gauss law. So the energy of placing an ion in dielectric medium can be calculated from the Coulomb potential. Delta G equal to Q prime del Q prime over var epsilon R. So the total work done, or Gibbs upon energy, just the integration from 0 to Q. So we have Q squared over 2 var epsilon R. Okay, so these are the potential energy for this ion. And it is used to estimate the free energy of placing an ion in a solvent with a particular dielectric constant. In this case, the water is hydrogen energy. Okay. So this one also we want to see that whether this ion is can easily dissolve in the that solution or not. Okay, so this one delta H G plus H. So we can see here the enthalpy increase with respect to the increase of the temperature. Okay, so the temperature increase, the enthalpy also increase. Meaning that what we can say is that when the temperature increase, the ion will vibrate much faster and producing more energy. Okay, so the difference between the self energy of two different value of var epsilon, and we estimate the free energy of transfer of ion between two medium with different dielectric constant. So here we see we have the same ion but with two different medium. Okay, so you see here the example, the transfer of sodium ion with R, the diameter equal to 0.95 Armstrong from water, where var epsilon 8 is equal to 80 to hydrocarbon medium, where var epsilon equal to 2, the potential energy difference is 0.15 times 10 to the power minus 12 uh, energy number. Okay, so here we can see that if we need a lot of energy to push the same sodium ion from water to the hydrocarbon. And inorganic ion are generally insoluble in organic solvent. Okay, so contohnya this one, ion does not containing the carbon. Okay, so this biomolecule, let's say the molecule does not contain the carbon, it will not dissolve in this organic solvent or the this, for example, the alcohol or the lipid. Okay, so we can see that this one we want to say that if we are chemist. Okay, so when we want to prepare the sample, so if we put the sample into the solution, some of the sample, if we use a wrong solution, then we cannot prepare the sample because the sample will not dissolve in that solution. Okay, so okay, and dielectric polarization keep ion out of non-polar environment. So non-polar environment, so there will be no ion will be out of that uh, solution. Okay, not dissolved in that solution. And it is extraordinarily difficult to move an ion into the interior of a protein or lipid bilayer. Okay, so here this one is we want to say that here if we have the cell, okay, so the ion, let's say a bad ion cannot enter our. It is quite difficult for that bad ion to enter our body, except from the tunnel channel. Okay, so next is the third one is the image force. Okay, so the image force meaning that the strong dependence of the self energy on the electric constant mean. So near a boundary, so if we have a membrane, okay, so the different solution, okay, solution A and solution B. So near a boundary between two medium with different dielectric constant, a charge will be attracted toward the region where a dielectric is higher. Okay, so it's moving to the charge is moving to a medium with higher dielectric constant. And the ion will have a stronger polarization action on the region with the higher uh, dielectric constant again. Okay, polarization action. An effective dipole created in this region will pull the ion toward the interface. Okay, so moving the ion uh, from far from the membrane to near the membrane. And an ion in high dielectric medium will be pushed away from a nearby low dielectric medium. Okay, so low dielectric medium will push this ion, high ion with high dielectric medium. Okay, so meaning that the ion will not pass through this uh, into this low dielectric medium. So these are from our textbook, so we can see our textbook. This one. So the potential energy of for Q and Q prime. So let's say this is Q and this is Q prime. So we have a distance of 2r. So these are distance 2r. So the Coulomb potential or the potential energy is equal to this equation. Okay, so the sign make the force point toward the with a higher dielectric. So if this one this is E1, this is E2. So the force is going to right. Okay, so with E2 plus E1. So E2, this E2, E2. So we have the same as this minus. So we have the potential moving to the right. Okay, so this on the example, the free energy of putting a charge Q at the very center of this picture or this interface. So Q G equal to this equation where this self energy, the first one is self energy in infinite medium, and the second term is the finite thickness reduce that energy. Okay, so this one. So so for the thickness of a typical lipid barrier of 50 Armstrong, the second term is negligible. So this one is can be ignored. Okay. So meaning that putting an ion into the middle of a lipid barrier is almost as hard as transferring it to a bulk hydrocarbon medium. So what we want to say here is that, or what we this text is going to say is that uh, it is quite difficult to for the ion to pass through our membrane or our lipid bilayer. Okay, these are again the another example. The circle, and instead for low hard is to be a charge residue in the core of globular protein is equal to this equal when B is large, so these are B, G equal to this equation, Q do the calculation. So and if E var epsilon H and var epsilon W, so these are hydrocarbon, these are the water. So it's the dielectric of water is greater than the dielectric of the hydrocarbon, so we can rewrite it as to this equation. So we have the charge A, the diameter of A and the diameter of B. So we can see from it is 1 A and B, or we play with this number A and B. So the conclusion is that it is almost difficult to place a charge in the middle of a lipid membrane or the middle of a globular protein, as it is to place in bulk medium with similar low dielectric constant. Okay, so here you see that the force, the potential energy is too high, so it will be difficult for the ion to move into this globular protein. A small pocket of water can stabilize an ion within an non-polarizable region. This cavity plays an important role in the ion formation. Okay, so from A side to B side. Okay, so the ion can pass through that membrane or that protein only through the specific channel. Okay, so we stop here.